indicated, there's a place on the screen where you can enter questions during the presentation, so please feel free to do so. Molly Dew, who is with HDR, will be moderating the Q&A sessions. The presentation will be available as PDF for download following the completion of the webinar. Details on how to access the presentations along with the responses to any questions which cannot be dealt with during the webinar will be emailed to the participants. Each webinar participant will be awarded 0.2 CEUs. In order to obtain the CEUs, the person registered for the webinar should download and fill out the CEU request form identifying all the participants. Once it is completed, it should be returned to the PNCWA. As Michael said, after the survey, there will be after the webinar, there will be a survey, and we would really appreciate you filling it out because that helps us determine what works and what doesn't work and what subjects we should be looking at presenting in the future. So with that, our presenter today is Joel Borchers. Joel is the construction coordinator for the Durham Advanced Wastewater Treatment Facility at Clean Water Services in Oregon. He's an Oregon Level 4 certified operator with over 25 years of experience in the design, construction, and operation of wastewater treatment plants. WEF is now calling those water resource recovery facilities, if you haven't heard that change. He is a member of the Oregon DEQ Wastewater Certification Advisory Board and is the past president of the Lower Columbia section of the Pacific Northwest Clean Water Association. He's also a member of the PNCWA Leadership Development Committee and the Plant Operations and Maintenance Committee. So with that, I will turn it over to Joel.
Well, thank you, Dick. As Dick said, my name is Joel Borchers, and we're going to go ahead and start the presentation here in just a second. I wanted to let you know that we're going to have 2 short breaks in the middle of the presentation so that we can handle any Q&A that comes up. And then at the very end, at the closing, we'll open it up for additional questions if you should have any at that time. So having said that, let's go ahead and get started. I wanted to give you a quick outline of how we're going to do this. We're going to talk about control systems with and without automation. We'll talk about the control system components, and then we'll dive into the PLC and the PLC components especially. We'll talk about the input and output hardware. We'll talk about process and instrumentation drawings as well as some control of descriptions. We'll talk a little bit about smart instruments, and then we'll wrap it up about PLC programming. I want to stress that this is a PLC basics class and that I am by no means a PLC programmer. My work in the construction of the treatment plants, I need to deal with a lot of instrumentation and okay, there we go. I need to deal with instrumentation, and I need to deal with the programmers. They have questions and issues that come up, and in the course of my studies, I needed to learn a little bit more. So during this presentation, there may come across a slide in which I need to actually try to read a little bit of code. That comes back and just, it will drive home the fact that I'm not a programmer by any means. I can get lost reading PLC code pretty easily. But like I said, this should give you a good basic fundamentals of the PLC basics. What you see right here is a schematic of a chemical day tank. It has a small chemical pump at the bottom of the tank, and it's pumping chemical out of the day tank into the process. There's a large transfer pump that transfers chemical from the large storage tank into the day tank. And right here, there's no instrumentation or anything like this. So what an operator needs to do is they need to keep a close eye on this process so that when that day tank gets low, they can start the pump up and begin to fill the tank up. And then as it's filling, they need to keep a close eye on it because they don't want the tank to overflow and get on the floor and cause a big mess, so they need to remember to shut the pump off. It takes a lot. It's not a very complicated process to do, but it can cause a lot of problems if the operator is not aware. They could actually run out of chemical so that the pump is not pumping anything, or during the transfer process they could overflow that tank and cause a great deal of cleanup issues. So even though it's not complicated, the operator needs to devote a lot of their time and resources to just monitoring that process. On the other hand, if you add a little bit of instrumentation and a little bit of programming to this, it simplifies the process entirely. When the level gets down to that low level switch at the bottom of the tank, that low level switch sends a signal to the PLC computer, which turns the large transfer pump on. And then that goes ahead and starts filling up the day tank. And then when that high level switch gets hit, then it sends a signal to the PLC, and the PLC shuts the pump off. Whereas on the first example, you required a great deal of operator observation and intervention. This method frees the operator up to do other things that are more applicable to their skills, so they don't need to sit there and babysit this process. This is completely operated. It doesn't take any operator observation at all. So that was basically a control system, and we want to talk a little bit about the components. There's basically 5 components that any control system needs to deal with. There's equipment, instruments, there's the communication network, there's the controller, and then there's the operator interface. And as you can see by the schematic below, both the instruments and equipment are wired directly up to the programmable logic controller, and it is responsible for all the control systems that go in. And then it relays that information to the operator interface so the operators can view and monitor and take control if they need to. We'll talk a little bit about all of these components throughout this presentation. So the first component we want to talk about is the equipment. And the equipment is any device that performs work or controls the process. I like to think about it as the control system's arms and legs. It's actually what's happening during the process. Some of those equipments might be blowers or pumps. You might want to open and shut a valve or a gate. You may want to turn on pieces of equipment. Anything that basically has an effect on the process would be a piece of equipment. And as in any type of equipment, you need to be able to control it somehow. And most pieces of equipment have some sort of local control station. It may be built onto the piece of equipment, or they may have a separate panel right next to it. And at the very basic control panel is just an on and off switch. If you don't have that, there's actually, you could actually maybe think of the plug going into the socket as a control switch if you needed to. Anything that's able to affect the piece of equipment would be a local control station. And a local control stations, a good local control stations has a variety of equipment on there. There's a local control switch which basically tells the piece of equipment where the control is coming from. There's a hand switch which basically tells the piece of equipment that the control is coming from the local control switch. But then there's also a remote switch, which is sometimes referred to as auto. It may be referred to as the PLC or the SCADA switch. Basically, remote is any control that takes place somewhere else other than locally. There's also the off switch, which basically means that this piece of equipment isn't being controlled anywhere at all. You could put that into the off if you were going to take a piece of equipment offline and didn't want it automatically started. Some PLC programmers actually use that switch to reset and acknowledge any alarms that are that happen in the plant, so that it forces the operator to go out to the piece of equipment, troubleshoot what's going on, and then they acknowledge the alarm by toggling the local control switch from auto to off and then back to auto. There's also various push buttons that might be on a local control station, a start push button or a open close push button, indicator lights that tell the piece of as you're walking by the piece of equipment, you can tell if the pump is running or not, or if the valve is opened or closed. There are opened and closed lights on a lot of valves, and sometimes when those are both lit up, that tells you that the valve is neither open or closed, that it's somewhere in between. It may be in transition, or it may have been stopped in the middle of the travel because you didn't need it either fully opened or fully closed, just a little bit. If you're running a blower or a pump that is speed controlled, there may be some sort of speed indication, an RPM gauge or a percent output gauge, and many types of some method of adjusting that speed. And anything that a person would need to control the pump or observe the condition of the pump can be put on local control stations. When PLCs were first put into the plant, a lot of people were really skeptical about PLCs and were really worried that the PLCs would crash and that they wouldn't be able to control the function. And so they anticipated an operator still being able to exercise local control over all of this equipment. And in some instances, that equipment may be spread over a larger geographic area. So what they did is they duplicated the local control station. So they put a variety of local control stations in one central location and called that a local control panel. And that allowed an operator to control a variety of equipment from a single location. As time went on, the PLCs have proven themselves to be pretty reliable, and that the cost and expense of having local control panels, really it was getting more and more difficult to justify them. Some plants still put them in, but more and more plants are finding that they really don't need those local control panels. In the unlikely event that a PLC does go down, the operators can go ahead and go from station to station and manually control a piece of equipment right at the very start, right at the very location where the equipment is. So that talks about the equipment. We'll talk a little bit about the instrumentation that goes on with in the control system. The instrumentation is actually if you go out and look at the process, you can, if you pour a sample of solids out on your desktop or your tabletop or something like that, you can tell the difference between a sample that is 1% solids and a sample that is 7% solids. You can tell whether or not you've got flow going down a flume, whether it's closer to 500,000 gallons a day or whether it's 5 million gallons a day. And you do that by your senses, your hearing, your sight, your smell, and touch. And that's basically what instrumentation is for. It detects a physical property of the process, and it takes that physical property and converts it into an electronic signal that can be used by a control panel or a PLC. There are physical properties such as chlorine residual. You may not be able to tell the difference between 3 parts per million of chlorine and 4 parts per million of chlorine, or a sample that is a pH of 7 or a pH of 8 by looking or touching it. But there are instruments that can do that. There are other type of instruments that you can use. There are flow indicators, there are level indicators, pressure, temperature, basically anything that you could use in place of your senses would be an instrument. So the communications network is what really ties all the equipment and instrumentation together. Its purpose, the communications purpose, is to move data between all the various components of the communications network. The instrumentation sends the signals to the PLC. The PLC looks at that and sends, passes that information along through the operator interface so operators can observe what's going on. It will actually send signals out to the equipment that will control the piece of equipment, whether the equipment needs to speed up or slow down, whether you need to turn a mixer on or off. It will actually tell you whether or not there is equipment, their status, how fast it's running, or whether the equipment's running at all. And the communications network, there's really 2 things about a communications network. Actually how it's constructed and how it's used. In the early stages of automation, it was nothing more than a couple wires, a couple copper cables that ran. As automation became more and more prevalent, they expanded into fiber optics. Now your smartphone can be a SCADA system, and you can actually get communications onto your cell phones because it can be part of the communications network. Or you can use your laptop computer somewhere and get on the internet and actually control and observe the process through that way. So there's the physical part of the communications network, and then there's how that information is transmitted along those wires or cables or wirelessly, how it's actually transmitted across. There are serial communications. RS-232 is one of the first methods that was used. It can be transmitted over the internet, over the Ethernet. There are some industry and vendor-specific protocols that can be used, and there are actually different types of field bus, Profibus and Foundation. Those are all different ways that messages actually get transmitted across the communications network. So the other part of this, that the instruments and the equipment all get transmitted through the PLC, and the PLC can actually take that information and take it to the operator interface. And the operator interface, let me go back a slide. The operator interface is actually the window into the process. There's little control that goes on in the operator interface as far as it doesn't usually have any smarts in it, but it allows an operator to take a look at the process, and by looking into that process, if if the operator needs to, it can actually give instructions to the PLC, and the PLC will pass those instructions along to a piece of equipment. So a good example would be that you have a tank that normally fills up, and when the level gets down, the transfer pump turns on and fills the tank up. Maybe you want to, for some reason, take that tank offline. So you can take manual control of that piece of equipment to prevent the transfer pump from filling the tank back up, and then you can take local control of the metering pump and allow that metering pump to bring that level down, so that when you take that piece of equipment offline, you have an empty tank. So that's something that's outside of the normal operation of the PLC, and that's something that an operator can actually come in and take local control of. So we'll talk a little bit about that. This is another good example of the way a control system is laid out, and it, you know, in the previous examples I had the clouds that had the different components on there. You'll notice that all the components are on here as well. The SCADA system, or the operator interface, is at the top. There's a communications that runs between the SCADA system and down to the PLC. And then there are communications network that goes out to each individual instrument and pieces of equipment through the communications network. So that's another way of looking at this, the control system. And we'll go into this diagram here in a little bit more detail. Go back talking to a little bit more about the operator interface. There are many different names that an operator interface can be called. Sometimes they're called HMIs or MMIs. Those and OIS, the operator interface system, those are pretty generic terms. They can refer to any type of man-machine interface, anything that allows the operator to have control. It can be referred to in those three terms. MTU is a master terminal unit, and I'll be the first to admit that I myself don't really understand what a master terminal unit, how that differentiates between any type of MMIS, or I'm sorry, any type of HMI or MMI. The operator interface I'm most familiar with is the SCADA system, and it's the one that's probably the most prevalent in all of the treatment plants. And we'll talk a little bit about the SCADA system. The SCADA system, SCADA stands for Supervisory Control and Data Acquisition. And the supervisory part of the SCADA system is basically it lets you observe what's going on in the process. The control system, as I said, how if you needed to take manual control, you could actually do that through the control system. But otherwise, you're basically letting a PLC do all the work. And the PLC is getting all this input and output, and it actually can record a lot of that data. If you wanted to get a past trend of dissolved oxygen levels in your aeration basin, for example, the DO sensors send that DO signal to the PLC, which relays that information to the SCADA system. The SCADA system actually records that data and maintains that data, so you can go back and look over a period of time to see what the DO levels are, and you can actually get a trend of the DO levels. So acquiring that data and retaining that data is instrumental to being able to actually troubleshoot the process and monitor the process to see that it's working well. An operator interface isn't really anything much more than just a computer workstation. The desktop computers that you have at your desk, we actually have out in the treatment plant that we use as SCADA systems. And they have a monitor and a keyboard and a mouse. If in some instances a trackball could be used in place of a mouse, but anything that allows you a window into the PLC is classified as an operator interface. There are panel-mounted screens and printers and keypads that can be put in so that it doesn't necessarily have to be a computer workstation as such. It can be actually built into the panel. When SCADA systems and MMIs and operator interface systems were first constructed, one of the very first things they created was something they called a mimic board. And what that was is when a piece of equipment would turn on out in the field, the on and off indicator lights had lit up at the local control panel. Well, they were able to come off those lights and run wires all the way back to a board inside the control room, and they would hook those lights up to that control board and then basically paint a picture of a pump, for example. So you could look at that board and see that that pump was lit up, and that would tell you that that pump was on. So that board would actually mimic what was going on out inside of the plant. That works really well unless, of course, you needed to do some changes, in which case you had a whole bunch of wiring that needed to happen at the same time. So it was one of the first operator interface systems that were constructed, but they very quickly tried to find another way of doing that so they could modify the control system if they needed to. And like I said, the operator interface system was the window to the process that lets you actually monitor the process. The operator interface system would be able to tell you if there are some processes that were getting out of limits, whether it was abnormal or a dangerous condition. Maybe, for example, your DO levels were reading 5 parts of oxygen in the aeration basin, and your normal set point for the DO in the aeration basin was maybe 2, 1.5 to 2, maybe even 2.5, but you knew that 5 was really kind of abnormal. So that let a person go out there and troubleshoot, maybe find a valve that was sticking or something like that. The operator interface would allow you to control the set point. Like I said, the set point in the aeration basin may be 1.5 parts per million, but maybe for some reason you wanted to have a higher level of dissolved oxygen in the plant. It's a very simple process through the operator interface system to just change that set point entry. And like I said, manual control allows you to take control of pieces of equipment for something that is not a normal configuration, taking pieces of equipment offline, or maybe bringing a piece of equipment online. Sometimes it's more helpful to have an operator do a startup in manual and then turn the process over into automatic. And then, like I said, the recording of the data allows you to create trends and reports and helps in troubleshooting. So the operator interface system really lets you have a good eye over the entire process and over the entire plant. And all of this stuff, the operator interface system talks to the PLC, talks to the controller, and so does the instrumentation and the equipment. They all talk to the controller, and normally the controller can be referred to in many different terms, but typical term we're going to use, at least today, is a PLC. And a PLC is a programmable logic controller. There are other names for them. There's a remote terminal unit and a distributed control unit. All of those have a different meaning about where control can be used, but a good generic term is PLC, a programmable logic controller, and we'll talk about how it came to get that name here shortly. But the purpose of any controller is basically to interface with the equipment and the instrumentation for inputs of process signals and output of control signals. So the PLC takes information, performs logic based on that information, and then sends output to the piece of equipment for control. And that also, like I said, it also passes along that information to the SCADA system, to the operator, so they can actually see what's going on, they can control it, and they can, if they need to adjust the set points, they can do that as well. So, you know, people ask, what is a PLC? And this is basically how a PLC control panel would look to most everybody today. There's through the top at the very left-hand side, there are the PLCs, the chips, and all those light gray slots there. Those are input-output cards. And then right below all those input-output cards is what's called terminal blocks. The darker charcoal gray colors, those are places for future cards that haven't been used yet. So that's what a control panel would look like today. But this is what a control panel looked like back in the 1970s, before PLCs were actually invented, and all the control was based on relays, and what was could be very compact now took on an awful lot of relays that look into play. And relays are a fundamental theme on control panels, on PLC. Relays and tasks, we'll talk a little bit more about that. But a PLC is really nothing more than a special purpose computer, and it's used to replace the use of the control panels. They figured out that they could do the same thing with a computer that they could do with the roots. Start to implement using a computer for the relay system. The problem is back in the 1970s when this really started going on, computers really cost a lot. And people were scared about computers. They were scared about the expense, and they were scared about the unknown of them. So when adapters first started using them, they said, well, I don't know what I'm going to call this, but what I want to call it computer. That will study off. The name finally evolved to a programmable logic controller. And so that's a fancy name for computer. It really isn't anything more than a computer, and you'll see that when we start talking about the components of a computer. Like a computer, a PLC has four basic components. There's the power supply, there's the processors and chips, there's the input and output, and then there's the communications cards. And you can equate that to any type of computer that you would buy at your local retail store. Power supply is part of a computer. The processors is the chip. Input that be your keyboard or your monitor. That's all input and output. And then there's the communications. Some computers, when they were first came on, they had external modems, and there were internal modems. And nowadays, modems are rarely used. They're not altogether not used. There are some instances in which they still need to be used. But there are communications used modems, or nowadays they use network interface cards. And these components can be in separate cards and just wired in to the chassis, or sometimes they'll be snapped together, or you may get an integral PLC, which is everything is a single device, and they call those brick PLCs, and I believe I will show you a picture of a brick PLC in a little bit. But like I said, most PLCs are modular in nature, and they're made up of different components that all come together to perform a single function. And it takes the input and output cards to receive data, send data back out, and it needs the chip to be able to process the data and know what to do with the data so it can send that out. And so it takes a variety of equipment and components to do that. However, all of that can be built into a single component. This is an example of a brick PLC, and up above on the left-hand side you can see all those a couple rows of indicator lights. On the right-hand side, there's the port that allows you to actually plug into the PLC and talk to it. If you don't have a jack that uses like the phone type jack, there are the other type of cables and plugs that you can turn into there, and then there's the terminal, the running or stopping of the PLC. But that's in a small integral PLC, which is just specialized for just a single process, and everything's built into it. And it's usually used for smaller applications, whereas the previous example showed it was built for expansion. And that expansion is basically uses a variety of things, and the first thing is a chassis. If you're buying a computer at your retail store, you're looking at the box, whether or not it's a large desktop computer or if it's a tower computer. That's basically all talks about the size of the box or the size of the chassis. And it's mostly passive. It really doesn't do anything, but it does hold the PLC cards in place, and it provides an electrical connection for the places to be those cards to hook up to. Some chassis come with a power supply inside of them. Some of them are external, and some of these components actually, like I said, they snap together or they plug in and don't require a chassis. They actually will mate right up to one another. As part of an expansion, you can get a jumper cable and actually interconnect the chassis so that if you need to expand the amount of cards that you need to, you can do that. And still, this system here has two chassis that have been interconnected, and they still left room for more expansion in the future if they needed to. So the power supply is the thing that it's like the gasoline for your PLC. It supplies the power. It's what controls, gives the chip the power it needs to perform its calculations. It's where the signal comes from to send the signal back out to the pieces of equipment and instruments. And it's one of the primary important pieces of the PLC, because you need to make sure that the power supply can provide adequate power for all the modules. And what it does is it takes the power that you plug into, and it converts that down to a low-level voltage that a lot of the PLC cards require. It also helps filter out some of the noise that's in the electrical current, and it protects against overvoltage. Overvoltage isn't good for the cards, so it's important. One of the things that is important to realize is that the cards and the power supply both can generate a lot of heat, and you need to be aware of that when you're constructing a control panel and finding out what the design is on the control panel. You want to make sure it's designed to ensure proper ventilation and that the thermal dissipation of the components is something that you can be aware of. So the processor is the chip or the brains of the PLC. And this is where the control logic is actually performed. You can see by this drawing is there's a battery backup. For some reason, should the power supply fail or if it should lose power, the battery backup will keep the chip running so you don't lose the programming that's in the chip. It also many times will include a communications port for programming, or that is where the SCADA system, the operator interface system, will plug into, and you can actually bring a laptop down and plug into the PLC right there, so you can troubleshoot right at the PLC in many cases. So the PLC processor usually is just the single chip that controls the normal functions, and normally there is only one. However, larger systems can have multiple PLC processors, and even some of the special function controllers, such as motion controllers, or maybe there's a piece of equipment that uses a special communications protocol. You can actually have a special communications controller or some type of other third-party controllers. When controllers first came out, the cost of memory was really high, so they tried to limit the amount of memory that the processors actually used, and sometimes they would only store the compiled portion of the program online, and that made it difficult for a programmer to troubleshoot, especially one that wasn't familiar with the system. Now, as the cost of memory has fallen, newer controllers store not only the compiled code, but the actual programming language and the comments are now located in the processor memory, so people can actually go in and read the programmer's comments, see what the program is trying to do, rather than just trying to look at the compiled code, which is it's pretty unreadable for anybody that isn't very highly specialized in that language. I don't know of anybody that can read compiled code, but I'm not going to say that there aren't those that can. So if there isn't any difference between a PC that you buy at the hardware store and a PLC, one of the differences is the cost. You can go down to your local your electronics supply store and or your local electronics retail store and buy a PC that's on sale for $600, whereas the cost for a full-scale PLC may run up to $30,000. I don't know the exact numbers there. I do know that PLCs can be incredibly expensive, especially when you're comparing them against a laptop. So why don't we just go ahead and use a PC for the processor just to save money. And the main reason for that is that the PLC components are chosen to take a beating. I mean, they can handle vibration, they can handle dust, they can handle temperature, they'll still operate in a severe environment. They may not like it, but they can handle it a lot better than your local PC that you buy at your local store. The other thing is that the PLC software has been built to be reliable, whereas the code in computers that you buy today is their emphasis is on the reliability of features. You know, get the newest PC because it can do this and it can do that and it can do this. A PLC says, I can do this one thing. The thing is I can do it very, very well. You know, if you look at PLCs nowadays, or let me rephrase that. If you looked at computers that first came out, the first release of Linux had about 10,000 lines of code, which sounds like an awful lot until you look at the lines of code that Windows 2000 had. It had 20 million, and compare that to the lines of code that Vista and Windows came out with. You know, 50 million lines of code compared with just 10,000 lines of code. They made it simple. They made it understandable. The less they put into a PLC, the less that you had that could go wrong with it. So it was built to be reliable and robust. Having said that, if you wanted to use a laptop or a computer that you bought for a PLC, you could go ahead. You could do that if you needed to. So, having said that, we're at the first break, and I want to ask anybody if you have any questions to please feel free to ask them, and I'll turn it over to Molly for right now.
Hi, everybody. Now we have the first break, and if you have any questions regarding what Joel just presented, you can type in that question module. I currently have two questions, and the first one is it true that a store-bought PC can function as a PLC? This is a simple one.
And yeah, I finished the presentation by saying that yes, if you wanted to, there is software available that can make a PC function just like a PLC. The issue is the type of application you're really going to use. If it's a critical process, I mean, you could use it in any type of process, but it certainly isn't recommended for a critical process. But if you have something that is a low-risk process, so that if it really doesn't matter or it doesn't have that big of an impact on about whether the process shuts down or not, then maybe you could get away with using a PC. And for an example, I guess I would say something like if you had a odor control system that was you set that up so that it could regulate the chemicals used in some sort of odor control system, and if it went down, what would be the consequences? Well, you could get odor complaints because your odor control system isn't working very well. Depending on the situation, that may or may not be a critical critical thing happening. You know, if the odor system goes down, that doesn't have a direct impact on the process. It may have a direct impact on your neighborhood, so that would be something you would need to look at. You'd have to just weigh the risk of having the process shut down against the risk of or against the benefit of against the benefit of having a lower cost, I would say.
Okay. The second question I have is, if I can control equipment through the SCADA system, couldn't I automate the process through the SCADA system as well?
Yes, that's possible, but again, that's really not recommended. For the same reason that you can use a store-bought PLC or a store-bought personal computer for a PLC, the SCADA systems are usually built and use the personal computers for those, and there's just too many, in my opinion, there's just too many things that can go wrong with a personal computer. I've left my computer on overnight and come back to work to find that it has been rebooted in the middle of the night because it performed an automatic upgrade on it, and when it came back up, it wouldn't have known to go back to doing that control. So it's possible that the computers could shut down, and also by keeping the control in one location, if you're keeping the control all focused in the PLC, when it comes time to troubleshoot something, you know where you need to look. A person probably wouldn't automatically go and look at the SCADA system to find out that the control of the process is being happened through the SCADA system. It's happening through the PLC. And actually, since the SCADA system needs a PLC to function in the first place, it just seems more logical to keep all the control in the PLC rather than in the SCADA system.
Okay. The third question is from me. You talk about the local control station and local control panel. And, you know, in my design, I also map both of these, you know, words. It seems like the difference is the local control panel is just for single equipment, and the local control station is just for single equipment. But local control panel can be like a mini PLC, can operate multiple equipment. But
Yes.
you know, yeah. But when you know, sometimes when we order equipment like screens, for example, in wastewater treatment plant, and we also ask vendor to provide the local control panel with the equipment. So in that case, is that local control panel function as a local station, or they're still it's more complicated, so we call it a local control panel? I guess that, you know, maybe you can differentiate these two just a little more.
Sure, and you know, you're absolutely right. There are vendor supplied systems that are made up of different components, and many times the vendor needs to supply some sort of control station to actually control the entire system. So in the instances where you are concentrating all the equipment in a single system, having a local control panel makes a lot of sense. Insofar as that we've purchased equipment before in which the vendor is required to, for their equipment to run, they actually supply their own PLC. And that panel, that local control panel, actually has their PLC located inside their local control panel, and then we take the signals from that PLC and feed it into our SCADA system. And in which case you have, where you have a vendor supplied pieces of equipment or a vendor supplied system, you're right, a local, that may be the overall difference, is and many times the local control panels have the PLC incorporated. In that case, it's perfectly appropriate to have local control panels in your plant.
I see. Thank you.
Mm-hmm.
I don't have any more questions so far. I don't see any question coming in. So if you like, I think Joel, you may proceed. And you know, everybody, if you have questions, you can keep typing in, and we can save it and to the next break, and then I can read it out to Joel and for the answers.
Okay. Hey, thanks, Molly. So moving on, we're going to talk a little bit about PCIO. And I/O is inputs and outputs, and that is what's used to interface between the equipment and the instruments. And inputs basically bring the process data into the PLC processor from the equipment and the instruments, and outputs provide a means of controlling the process out to the equipment and instruments. And usually I would say that inputs are usually coming in from the instruments, and outputs are usually what's going out to the equipment. I say that, but as I'm saying that, I realize that there is a lot of equipment out there that actually needs to send information to the PLC to give an update of the status. For example, you'll have a pump that actually sends a signal to the PLC to tell you that it's actually running, or you may have a valve that is actually opening or closing, and it's telling the PLC how open or closed it is. So, but the outputs is the data coming from the PLC. The inputs is the data going into the PLC. And that's basically the difference between the two. So there are a variety of ways of getting this data to them. You know, there is the upper left-hand picture on your screen there shows a terminal card, and you could actually go and wire your instrument directly up to that terminal card if you needed to. The problem is that if you needed to take that card out, you would need to undo all the wires, and then you need to be responsible for making sure they were wired correctly back. And with all those field wires going into the terminal cards, you can get quite a cluster, which is what you see on the right-hand side of the picture. Is you've got all those cards are going up there. It's kind of a mess. So the ideal situation is to have a set of terminal blocks, and field terminal blocks, they use those to make the conductor terminations easier. We can have the instrument techs take the wires from the cards and run those down to the terminal blocks, and they can take their time. They get nice, neat installations so that when the contractor or whoever is putting the instrument in, they can just wire up to the terminal blocks, and that makes the connections easier to happen, and it also can accommodate some of the larger wire sizes. There are slot fillers. We've seen those before where you've got a spot for cards, but you don't have the cards available, so you just put in these slot fillers, and they're used to fill empty slots in the chassis to keep dust and debris from collecting on the connections. I said the PLCs are robust, that they can operate in pretty harsh conditions. However, dust and heat are their two main enemies, and you want to try to combat that if you can. So using these slot fillers, you can help keep the connections clean. We'll talk a little bit here about instrumentation and control diagrams. Actually, they're called process instrumentation drawings, P and IDs, and this allows anybody a good overview of the control system itself, and we'll talk about that. The most important sheets in a series of P and IDs are usually the first couple pages, and that's the legend. That actually tells you, gives you the information that you need to help decipher what goes on in a P and ID. And reading P and IDs really isn't very difficult. I will say it does take a little bit of time, and the first couple times you do it, it's kind of overwhelming when you see it, because it's just, if you're not used to reading them, it looks completely foreign, and it really is hard to figure out exactly what you're looking at. So you try to, especially when you first start looking at them, you're referring to the legends quite a bit at the beginning. And that tells you exactly what the symbols are, how the instruments are named. It gives you some of the commonly used abbreviations. And so when you first start looking at process and instrumentation drawings, what you probably want to do to start off with is just trying to trace along the flow and find whether or not it's a liquid flow, a sludge flow, or maybe an air flow. You want to trace the path that flow is taking, and that will allow you to see what's going on. Pretty soon, as you're tracing along, you'll see a device that is called out, and you may, PIT, and you're wondering, well, what the heck is a PIT? And you go back and look at your instrumentation, and you'll look it up, and you'll find out it's a pressure indicating transmitter, and you're going, oh, okay, it's a pressure gauge. So as you trace all this stuff out, you'll look at that PIT, and you'll notice, okay, that's going up into the PLC, and then you can see above that how that data is actually relayed up into the operator interface system. So the more you pick it out, the more you trace it out, the more you look on refer back to the legend, the easier it will be. When I first needed to learn how to read P and IDs, I printed off the legend sheets, and I kept those right in front of me while I was looking at the diagrams, because it was so foreign. And I still, from time to time, need to refer to the legend. There may be a unfamiliar abbreviation, an unfamiliar flow stream, maybe unfamiliar valve or pieces of equipment that I'm not used to. So I'll go back and refer to the legend. I will say it's a lot like a foreign language, that the more you use it, the less you need to refer to the legends. But when you first are reading PNIDs, you need to refer to them a lot, and they're really full of good information to help you understand how the process works. And this is just an example of what a PNID looks like. The very top portion of the screen there shows all the information that is being relayed to the SCADA system and to the operator interface. The block below that is actually the PLC itself. What information is being relayed to the PLC and what information actually goes into the PLC. And if you look real carefully at the diagram here, you'll notice that all the if you look in the PLC window there, you'll see a bunch of arrows underneath those little boxes, and all those arrows point into the boxes. That shows you how there is all that data is input going into the PLC. And if you look on the right-hand side there, the very first box on the left there looks like that arrow is pointing down. So that's going out of the PLC. So that would be an output. So that's all what's going on in the PLC. And then below is what's actually out there in the field. You can actually see pieces of pumps. You can actually see tanks, and there are flow meters and valves that are located down there. And so the more you, excuse me, the more you look at these and the more you can trace out what's going on, the better off you're at. Normally, when you read a PNID, you read it from left to right and from up to down. If you go to the left, you can actually start tracing things out until you get all the way to the right-hand side, and then there's a arrow and a tag, and that refers you to another drawing, so you can actually go to another drawing if you need to and trace that out and find out where the information is going from there. One thing I kind of wanted to point out is in some instances the line or pipe may not be fully drawn out. Up in the upper right-hand corner of the large window there, where the dark line is, you'll see that the arrow goes and it ends with the number 1. And if you trace that out directly across, you'll see that that 1 picks up there, and so that tells you that the line is continuous. They didn't draw the full line because it would have been in conflict with some of the other drawings they were trying to show you. So the more you look at these drawings and the more you tease out the information you can get from them with the legend, the more you'll see that there is an awful lot going on in these drawings, and it's what the programmers and the designers use to communicate back and forth and how that's used. And this is basically a visual representation of what is going on. So that can give a programmer an idea of of how the system should work. It works especially well if the programmer knows the process along the way. But many times PLC programmers, while they are very good at programming PLCs, the programmers really don't know the wastewater process as well as you might. So in that case, they need a lot of verbal instruction. And for that, they need what they call a control loop description. And this is a blank control loop description, but it has the information that a PLC programmer would need to know in order to write the PLC program. They give you, it starts off basically with a short description of the process and how the process is designed to work. The last update, a lot of times when these are being created, they go through numerous revisions. So this tells you when the latest date and sometimes latest date and time that the control loop description is, so that the programmer can make sure that they're working on the latest control loop description. It starts out by listing all the equipment that's being used on the control loop drawing. It talks about all the instrumentation that's available. The tag number is a method of identifying the piece of equipment in the PLC program. It tells you a little bit about what type it is. A good example might be an equipment name, maybe primary effluent flow meter. And then the tag number may say FIT dash and then a series of numbers. And it may tell you that the FIT lets you know that it's a flow indicating transmitter. The type may tell you what type of flow meter it is, whether it's an ultrasonic or whether it's a propeller flow meter. The range gives you an idea of whether or not we're talking about gallons per minute, or if we're talking about million gallons a day. Gives people just an idea of what they're talking about. And then we talk about the control strategies. And the control strategies are the various different methods of control. There's a local control station that it uses that area to explain what's located on the local control station. You know, there's a local off remote control switch. There are on and off push buttons. You know, and under this section, you would talk about the local control station. In order to operate, the switch needs to be in local. The on push button will start the piece of equipment, and the off push button will stop the piece of equipment. So that gives the programmer knowledge of how they need to program that. They need to allow for that to happen. The VFD control panel, many pieces of equipment don't have a VFD, so under that you just put not applicable. However, on some pieces of equipment, for example a pump, you may say that the VFD control panel, in order for that to operate, the local control switch at the local control station needs to be in remote, and that this basically gives you the instructions on how to operate something at the local control panel. The motor control center may not have anything else other than a power switch, but you say in order for that piece of equipment to run, there's the power switch needs to be energized. Maybe there's an overload reset button on the bucket at the motor control center, so you would want to say that you'd want to describe that reset switch and what it's used for. Manufacturer's Control Center, Molly asked a question about this. Many vendors will supply a system, and they will have a control panel to operate that piece of that control system, which would operate various components in there. So that may be a control center that is supplied by the manufacturer. Okay, I talked about the control station already. That's in error there. I need to talk a little bit. That local control operation alarm reset basically is a description of how the operation would be. Then when you talk about the local control station, you would talk about how you control at the local control station. We talked about local control panels. In this document, it's referred to as an intermediate control panel. If it's applicable, you would go ahead and talk about how you would control the equipment from the local control panel. And that's the first part of the local controls description. It goes on from local control, and it talks about SCADA control. And it talks about how you're able to place the piece of equipment in SCADA manual so that you can actually control the pump or the piece of equipment manually from the SCADA system. So that even though the level down in the tank, even though the tank is only halfway full, if you want to, you can put it in SCADA manual and start it and fill that tank back up. Or maybe you put it in manual because you want to prevent the transfer pump from filling the tank back up because you want to pump the tank down. SCADA Auto is when you just return control back to the PLC and it runs the way it's been programmed. Then we talk a little bit about the SCADA display, and we talk about what an operator can see when they bring up the SCADA screen, what the status of the equipment is, whether or not it's running or not, whether or not it's in local or remote. Going back up to where it says SCADA manual and SCADA auto, if you were to put remote manual and remote auto, that would probably be more accurate. But down at the SCADA display, that actually tells you what you get to see. The operator entries actually gets to tell you what you get to change from the SCADA terminal, so that if you wanted to say up the set point for a certain parameter, you could do that through the SCADA system. There are alarms that the SCADA system can tell you about, and at our plant we group those into two types of alarms. There are informational alarms, and then there are critical alarms. Critical alarms actually demand a response of some sort. Be an acknowledgement. Sometimes we say that the critical alarms are what goes through an alarm notification system. We actually have two-way radios that can, and we can have alarms that go through the two-way radios, so that while an operator is out in the plant doing work, if there's an issue that comes up that needs their immediate attention, that alarm can actually go through. A critical alarm would actually go through the radio system to let them know. There are hardwired interlocks that can be in the control system. You may have a positive displacement pump, for example, and you may have a pressure switch that is wired back to the bucket, so that if you try to start up a pump against a closed valve, that high pressure switch would actually go to the bucket and trip that bucket out. That would be a good example of a hardwired interlock. In that case, it doesn't matter whether you're running that pump in local or whether you're running that pump in remote. It doesn't matter if you're running it in remote manual or remote auto. It will not allow you to run that pump because the discharge valve is probably closed, or there's some sort of blockage there that's causing high pressure in the discharge piping. There are software interlocks as well, and software interlocks usually only operate when you're operating the piece of equipment through SCADA. So a good example is even though you're in SCADA manual and you're pumping down a tank, it may only go down to like 2 feet before the pump is actually shut down because the programmer actually put in some safety. They don't want to allow you to run that pump dry. So what they'll do is they'll put a software interlock that says if the level of that tank isn't any more than a certain amount of feet, that the pump won't run. So that prevents you from running the pump empty. And the only way to really get around those software interlocks is to go down and actually run the pump locally in hand. There's usually a way to get around software interlocks, but you have to remember that they're there for a reason. Historical trending is something that's important. The PLC is getting all sorts of inputs coming in from the SCADA system. The programmer needs to know out of all the information that it's getting, what does it need to retain. And so it allows you to the historical trending section tells them, for example, is that anytime it gets a DO input that it wants to retain that, so that you can go back and look and find out what the airflow is. It's a good way of telling the programmer what information to keep and what information is really only needed at the time of running. Equipment failure sequence and equipment automatic failover sequence. There's sometimes not a lot of distinction between the two. The equipment failure sequence will tell you what will happen when a piece of equipment fails, what's going to happen and what you need to do to get it back online. Sometimes there's an automatic failover sequence, which basically says that if this piece of equipment shuts down, the other piece of equipment, this piece of equipment shuts down on a failure, this piece of equipment actually there's backup equipment that will automatically come on in its place. So that's where you would talk a little bit about automatic failover sequence. If this fails, this will pick up the slack. So that's a good description of the control loop description. They're good to have and they're good to be familiar with. They can tell you a lot about how a piece of equipment, how the PLC has been programmed to run the equipment. So we'll talk a little bit now about inputs and outputs and about what the difference is. The PLC is required for, has a variety of things that come in and out, and we'll talk about the two major types. We'll talk about them as inputs and outputs, although they're really too similar. I may skim through that pretty quick. The digital input or the digital output really can be in only one of two states. It's either open or closed. It's either on or off. It's either energized or de-energized. It may be like a flow switch. It doesn't tell you exactly what the flow is, but if you say get below 5 gallons a minute, that switch will turn on to let somebody know that you're getting low flow. It may not tell you exactly what the flow is, but it will tell you whether or not it's opened or closed, or I'm sorry, if the flow is high enough or not. you'll also use those digital inputs to tell you if a valve is all the way open or if the valve is all the way closed. So, like I said, it can be in one of two states. And what you can do is, if you have enough digital inputs, you can actually combine those so you can get more than just an open-closed information. For example, if you look at this, at the digital input, to be fully closed, it has to tell you that it is closed, it's energized, and that the midpoint is energized. The open is not energized, and the error point is not energized either. So well, no, excuse me. Let me rephrase that. Let me go back up. No, I'm right. If it's all the way open, well, I'm sorry. If the digital input is fully closed, it will show it's fully closed. It will show that it is not open. That's what you really need to know about. And if the input is showing fully closed, if the number 2 input is showing fully opened, then the fully opened switch is opened. So by looking at it, if you see that the fully closed input is all the way closed and the fully open input is showing all the way open, you'll know, for example, that it is probably somewhere in the middle. That's what this table is trying to show. It's always showing voltage, and in this case, it's showing opened and closed, so you'll know that it's in the middle. It's either transitioning from open to closed, or it's only partially open. And they do that because they want to, if you used one input just to show, if you showed it that it wasn't opened or closed, you could maybe assume that it is in transition. The problem is that if there's a problem out in the field, like a blown fuse, for example, you wouldn't know that because you're not getting an indication back. You really want to try to get indication back from the field. Absence of indication doesn't necessarily, absence of an indication should tell you that there's a problem. And so that if you have an absence of voltage, you need to know that there's a problem out there, and they need to go find out what that problem is. So I guess the crux of this whole slide is that you can actually put together a series of inputs to get some multi-state status if you needed to. I'm going to skip right over the digital input or digital output because it's the same thing as the digital in. This is what is getting information taken in. Digital out is information going out. So the digital input is the valve or the equipment telling you what it is. The digital out may be telling you, the PLC telling the pieces of equipment what status it wants to go to. If you're sending a digital out, you may be telling a valve to open, or you may be telling a pump to turn on. So that's what the digital output does. It does the same thing as input, either on or off, open or closed. And the same way we talked about multi-state outputs. The analog input, excuse me, is a little different. Is that it gives you the opportunity to give you a value somewhere between 0 and 100%. So for example, I think, let me just go on to the next slide and show that this is a diagram of a flow indicating transmitter, a flow meter, and it is ranged from 0 to 500 gallons a minute. And what that does is it sends a corresponding 4 to 20 milliamp signal to the PLC card that takes that value and converts that milliamp signal into a numerical value. And once again, you notice that the difference between 4 and 20 is 16. If you break that down, you'll find that half of 16 is 8, half of 8 is 4, half of 4 is 2. You get down to 1 and 0. Like I said, when you're dealing with computers, everything's either a 1 or a 0. So that's one of the reasons why it uses 16. The reason it uses 4 to 20 instead of 0 to 16 is because, once again, you always want to have some sort of voltage in your system just to know that your system is active. And there are other signals that equipment can give out. Some instruments give a voltage out rather than a milliamp signal out. We try to use milliamp signals when they're available because they're the most common and they give better noise immunity than voltage signals, and especially if you're going a long distance. On some instruments, using voltages, if they're going for a short distance, maybe a voltage signal is okay. But if you're trying to transmit over a long distance, you're going to want to use a milliamp signal. But on this, for example, 4 to 20 is 16. Half of 16 is 8. So if you add 8 to the 4, that gives you 12. So if it was going to give you, if the flow indicating transmitter was sending a 12 milliamp signal to the PLC card, and you knew it was scaled 0 to 500, you knew that the 12 milliamps is halfway between the 0 to 500. So you would know that the flow indication is somewhere around 200. Well, if everything's calibrated right and dialed in, you should have 250 gallons a minute going through that flow meter because you're getting a 12 milliamp signal. And a digital output, or I'm sorry, an analog output is the same way. Sending a 12 milliamp signal out to that valve, maybe telling the valve that it needs to open halfway. If you look at this whole, if you look at the whole system in particular, you'll see that the flow indicating transmitter is sending an analog signal into the PLC. The PLC is comparing that and saying that, you know, maybe that flow needs to be, isn't up to set point. Maybe it needs to, you need more flow. So it's going to send an analog output to the valve, telling the valve to open up a little more to allow more flow to go through, and that will fill that tank up. And then that level indicating transmitter at the very right-hand side, at the very end there, sends an analog input to the PLC and gives the PLC an indication of how full it is, and that when it gets to a certain level, it sends a digital output to the motor control center, which actually shuts the pump off. So that's how those signals actually work. And I'm going to skip over that because we've talked about analog outputs and 4 to 20s. That's basically a rehash of the same thing. We'll talk a little bit about, there are some instruments that instead of using a 4 to 20 milliamp signal, they actually have their own signal protocol that can actually send the information directly to the PLC. So if you look at that flow indicating transmitter, that type of line that's going up to the well, it's showing SCADA, but that's actually going up to the PLC. That is sending instead of a 4 to 20 milliamp signal, it's sending a signal that says I'm at this flow rate. So it doesn't need, you don't need to convert that. It tells the PLC exactly what the flow is. And also for example, this will, the information, the PLC can actually send an information to the valve that says, open up an additional 5%, for example. And then the level indicating transmitter doesn't say it's at 100%. It tells you it's at, 4 feet, for example. And it's a more sophisticated method of communicating with the PLCs, not widely implemented at this time, but becoming more and more prevalent as time goes on. There are some advantages to using smart equipment. You can transmit multiple devices using a single wire, so you can use less wiring. You don't need those multiple I/O cards, and it often provides access to additional information that you can use for tuning and diagnostics. Some of the disadvantages is that since they are rare, they are more expensive. They're not widely used. So as the use becomes more prevalent, I expect the devices to come down in price. The setup may be more complex since they're fairly new. A lot of the setup may not be well ironed out or very simple to understand. It's complex, but they're usually well documented, and the setups are complete. You just need a lot more training on how to do that. The major disadvantage, I think, though, is that if you lose a single cable, you might lose multiple instruments. So that's something you need to consider very carefully and find out what the chances are of losing that cable and what to do in that place. This smart equipment, it's very common nowadays for PLCs to have this smart equipment in there. Less so with more of the instruments. However, I will say that I've seen more and more instruments becoming capable of having some of this smart technology. We're getting near the end, but I want to take this opportunity to ask if there's any questions at this time. Molly, are you still there?
Oh, I'm sorry. I'm back on. I just clicked mute just now.
Oh, okay.
Apologize. Yeah,
That's all right.
I'm back on. And yeah, here's our couple questions I received. And the first one, why is that the local readout on an instrument or piece of equipment doesn't match up with what the SCADA readouts say?
Well, there could be a couple of reasons for that. What comes to mind right now is that it may be a scaling issue, whereas the local readout, we'll use, I guess, level as an example, is that you may be reading 4 feet in a tank, and when you go to the SCADA system is reading 12, and you're wondering how that's possible because you've got an 8-foot tank that's maximum feet. It may be just a problem that the scaling is incorrect, That's a common issue that you run across usually when that's first getting set up. And there's some of the there's some instances where the local readout may be very precise. You know, you may have a level of 4.256 feet, and if you look on the SCADA screen, it's reading, you know, 4.3. And what's going on there is it's just not reading those significant digits, and it's probably just rounding up. If there is, but usually if they're quite a bit different, there's usually a scaling issue.
I have one more question, but Joel, I think the time is close to 10:45. Do you want to save that question to the last when you finish all the presentation?
Yeah, I see we're getting near the end, so why don't I just go ahead and move along?
Okay.
Thanks. We'll talk a little bit about PLC programming, and this is really where I fall a little bit short as like I said, I'm not a programmer, but I can tell you a little bit about that. Is that initially PLCs were relay control panel replacements. The control used to be using relays, and the PLCs are replacing those relays. And relays are basically use a set of contacts inside that are either open or closed based on how power is supplied to them. You can either have a normally closed contact or you can have a normally open contact. And right above that diagram, I'm showing a push button relay, or a push button, and basically it shows that relays usually can either be opened or closed depending on how you wire them up. If you were to use the set of contacts that are up at the top, you're going to have a normally closed contact. And when you push that push button, it opens the contact. But if you were to wire those at the contacts at the bottom, and you would have a normally open contact, and when you push the button on there, you'd have normally closed contacts. So depending on how you wire them up, contacts can either be opened or closed. And what I wanted to show here is this is the first ladder logic diagram you'll see, and actually this is an electronic wiring diagram which shows a couple push buttons, and there's a start push button and a stop push button. And you have to remember, if you look at these wiring diagrams, power goes from left to right. And so that when you push that start button, push button, that will allow power to come across, and it will go through the stop button, and it'll come to this contact relay, and it'll energize that relay. And when that CR1 is energized on the top rung, that bottom rung, which is a match for it, CR1, becomes energized. So once you hit the start push button and complete that circuit, when you let go of that start push button, that circuit maintains contact, so it stays energized. And when that CR1 is energized, the CR1 below that as well is energized, and you get that motor to actually run. So pressing that start push button starts the motor, and when you let go, the motor continues to run. As soon as you press that stop push button, that closes all the power to that CR1 coil at the top of there, and that de-energizes that. That causes those contacts to open, and the motor closes. And so that was a wiring diagram. They did the same thing. They used ladder logic because the plant personnel were familiar with ladder logic, and it allowed them to understand how to program because the ladder logic diagrams were very similar to the wiring diagrams. And so with the PLC programming, it's contacts are one of the most common programming functions. And we talked about them being normally open or normally closed, and that's usually how they are written, as the one on the left shows normally open. The one on the right with the line going through it, that's the symbol for a normally closed contact. And the momentary contacts, those are usually like push buttons or a spring-loaded switch, momentary contacts. Coils are energized when power flows to them. So that's why that CR1 at the top is a coil, and it's energized because the start contact's closed and let the power run, or energizes that, and that closes the switch, the contacts below. There's contacts and coils. Contacts actually need to be opened and closed. Coils, whenever they got power going to them, they automatically close. The coils can actually close contacts as well. Boxes, there are function boxes that can actually perform math or perform counters and timers. We talk about AND and OR operations. If you look at the top screen, you'll see that in order for power to get to that Q0.0, 10.0, and 10.1, power has to go through both of those. So that's the way you perform that option using contacts. There are AND programming boxes that basically sends the signals in to the AND box, and if signals are both coming into the AND box, then it allows the power to come through and energize the cube or 0. So that's what an AND operation does. This OR operation does the same things, or does similar, but in this case, either 10.2 or 10.3 need to be energized for the power to run through. And similar with the OR box, if either one of those 10.2 or 10.3 is true, then power goes through it to do that Q0.1. So that's how OR operations are handled. So if you look at this, Q0 will be true when, so it's either 10.2 is true or 10.3 is true, but in either case 10.4 would also have to be true as well. So that's how that can be written. And ladder logic diagrams, I said that when I'm having to read code, that my skills are really not adept at this. So what I will say is that one of the great things about PLC ladder logic diagrams is that it provides you the ability to easily modify the control scheme and to enhance the control features, so that maybe that timer wasn't there at the time when the system was first constructed, but it was very easy to put that timer in the future, so it didn't require a bunch of extra wiring. Running out of time, I'm going to talk a little bit about these. Is that normally closed contacts usually are written as, when you read them, they say not. So that digital input is not activated, so the power will go through. the D1 and D2, the second line, that's an and, that's an or, and the third one is a combination of all of them. There are two methods of programming PLCs, excuse me, either online or offline. When you're programming online, you are programming code right into the PLC, and usually those aren't executed until they're tested and compiled. I will say that in some PLCs the code is interpreted, which means that it's read and then converted just before that. So you need to know whether or not your PLC is interpreting code or compiling it. Once it's compiled, then it's executed. If it's interpreted, it can be executed just as soon as you enter it in. But that's all with online programming. With offline programming, you actually can enter the code in, you can verify it and check it, and once you're happy with it, then you upload the programming to the PLC. So upload is sending information to the PLC, download is getting information back from the PLC. I'm about out of time, so I'm not going to go into this very much as to tell you that there is an analog control, ratio control, which basically allows you to tell the PLC that, for example, for every million gallons coming in, I want to send so much dosage to the pump. You want the pump to pump so much, and it's a ratio. It's commonly used for dosage flow. Process variable is usually the analog value that's being measured. So that's what you see out in the field. The set point is actually what level you're actually reading, and the output is a product between the process variable and the ratio set point. So we'll talk about that a little more. PID control, this is, rather than go into this, I will let you know that PID control stands for proportional, integral, and derivative. And proportional basically gives you a change based on the difference between what you want and what it is. And that is the main type of control that usually is the PLC. It's the one that should handle 90% of the control system. The integral, actually what it does is it accumulates the error between the two so that it can help you fine-tune the proportional control. And the derivative basically concerns yourself with the amount of change per time unit, so that if you see something that is changing very rapidly, you may need to enact some type of control to help dampen that out. I'm going to just blast right through this stuff really quick to tell you that the derivative term helps get output, gives you a jump on the changes when they begin. The derivative is very common in positioning applications. However, you don't see it very often in water or wastewater. But the PID control is a main type of control used for PLCs, and once they're been instituted, they need to be tuned. And by tuned, it helps you depend on how well do they actually dial in to your set point that you want. The classic critically damped process usually has the value overshooting the set point a little bit, coming back down, maybe undershoots it a little bit, and then comes back in and actually dials it in fairly quickly. In many instances, you don't really need to get to set point that quickly, and it's not that critically that it be exact. So a lot of people will actually over dampen their control loops so that it will take a long time to come up to set point. Yeah, a long time. It will take longer to come up to set point, but may not actually reach set point at any one time. And then there's the under-dampened control loop, which has usually the error is increasing and the error decreases over a time, but it can take a long time to dial in which that it keeps overshooting the set point, but eventually gets it dialed in. It's a process that probably not desirable. If I had to pick the two control loops, the tune, I would prefer one that was critically damped or perhaps over damped to one that was under damped. The critically damped gives you control quickly. Talked about those, and that's I realized that I really blew past the P&ID control, which is probably just as well because I'm not as familiar with that as I would like to be, but I gave you a basic indication of what they are. So having said that, I will open it up to any questions that you guys have for now.
Thank you, Joel. It's a very informative presentation. I here receive a couple more, and if you have more, we have about 2 minutes to 11, so probably let's just start with the ones I have. And the first one I have here is, can the same ladder logic that is used to start and stop equipment be used for filling or drawing down a tank?
Yeah, it actually can. That's one of the nice things about programming is that there are a couple different control loop scenarios or programming functions. It's like any type of programming. You use ands or ors, and they can be used in a variety of different ways. And the same method that you can use to start and stop a pump or a piece of equipment, you can use that for starting and stopping base. Instead of using a push button, you would use level switches or level indication to fill or draw down a tank.
Okay, the next question is ladder logic the only PLC language available?
No, not really. It's by far the most common because they, when PLCs were first developed, it was for the electricians and instrument techs were usually the folks that were responsible for programming them. So the developers made the ladder logic program really similar to the wiring diagrams. But now the PLCs are becoming more and more common. There are people that are becoming more and more specialized in the programming of PLCs, and in some instances there are people that really didn't know much about PLC programming, but knew enough about computer programming that they could take those skills and move those over into programming languages. So there are compilers that will use C++ or Visual Basic, but in all honesty, they're not widely used. But I'm expecting that as this field continues to develop, I mean, it's 30 years old, 35 years old right now. But as it matures and as it continues to mature, I think you'll find that there's more opportunity for different languages to be coming into the PLC programmers.
Okay. I think the last question is for everybody. Is where can I get more information?
Well, that's a good question. I took most of this information I passed along was from just peering over the shoulder of a lot of the programmers. I did look at YouTube, and there are some good courses on YouTube, some good videos to help you understand PLCs and to help understand PNIDs. Sometimes you can check the community colleges. Sometimes they'll have some type of industrial computer applications classes you can take. I noticed that ITT Technical and the Phoenix College both have PLC courses along there. But if I had to recommend, if somebody really wanted to get a good background on instrumentation and control, the Perry Technical Institute in Yakima, Washington has an outstanding program for people who are really interested in following up and maybe making PLC programming a career for them. Okay,
we're running out of time, and we're probably a couple minutes over, 11. But I think I personally think it's a very good presentation. And thank you so much, Joel, for the presentation. And thank you everybody to attend the PLC Basic webinar. And I think that's all we have for today.
Well, I'll hop in for a second just to answer or to add on to Joel's response. The Water Environment Federation has a manual of practice on automation of water resource recovery facilities. It's Mach 21. So that has a lot of really good information if you want to dig into it. It's a fairly expensive book, but it's a good reference book for your plant library. And I guess with that, just like to thank everybody for joining the webinar, and to remind everybody that there will be the questionnaire. So please, after you log out, it'll come up. So feel free to fill it in and tell us where we've done well and where you'd like us to go in the future.
Thank you, Dick, and thank you especially Joel and Molly. This is Michael in the PNCWA office. Thank you all of our attendees. You will see that evaluation pop up as you exit the webinar. And 1 hour after the end of the webinar, you should get an email with a link for CEU attendance. If you missed that email, you can ask me to resend it again. Thank you all.